This is how digoxin works to increase the force of contraction of cardiac myocytes. Here I've represented the myocyte as this blue box, and inside the cardiac myocyte is the sarcoplasmic reticulum, which is a store of intracellular calcium. Notice the ion concentrations. We have low intracellular calcium, low intracellular sodium, and comparatively high potassium, whereas calcium inside the stores is also high. I've tried to represent that by the relative sizes of these fonts. Here I also show the contractile machinery in the form of the actin-myosin, and this is the contraction of a single twitch in the muscle fibre. Calcium is kept low because calcium is a key signal in all sorts of intracellular processes. There's two ways it's kept low intracellularly. It's pumped into the sarcoplasmic reticulum, but it's also pumped out of the cell using the sodium-calcium exchanger. The sodium-calcium exchanger uses the inward driving force on sodium ions to push calcium ions out of the cell. Where does this driving force come from? It comes from the sodium-potassium pump, which pumps potassium into the cell and sodium out, causing the concentration gradient which drives the sodium-calcium exchanger, which keeps intracellular calcium low. Now let's see what happens when we add digoxin. Digoxin binds to the sodium-potassium pump, and specifically it binds to the potassium binding sites. And what that does is it stops the sodium-potassium pump from doing its job as effectively. The result of that is that the intracellular levels of sodium start to rise. We now have a reduced driving force on the sodium. So that means there's less of a force turning this sodium-calcium exchanger over, which results in a rise in intracellular calcium. That will affect the actin-myosin interaction, with the result that the force of the twitch contraction increases. But there's another thing that happens as well, is the calcium interacts with the ryanodine receptors on the sarcoplasmic reticulum, causing them to open. So we now have a release of calcium from the intracellular stores, and that results in an even greater increase in intracellular calcium, and that in turn means an even greater increase in the strength of the twitch. So you can see that what digoxin is doing is it's reducing this driving force, and by two routes causes an increase in intracellular calcium, and that causes an increase in the strength of contraction, and that's helpful in heart failure to restore cardiac output. Notice that there's another consequence of digoxin competing with the potassium, which is that if extracellular potassium is low, then there is less potassium competing for the digoxin site, and so digoxin becomes even more effective. What that means is that a patient with hypokalemia, that is low potassium levels in the plasma, should not be given digoxin, because then digoxin becomes so effective that we have too much of a degradation of the gradient, and that can be toxic.